so the first objective for today is a holdover from last time because we didn't finish. We want to continue describing natural radioactive decay. Specifically, we want to talk about beta decay and gamma decay. Then we want to describe the ionizing properties and penetrating abilities of those three decay products. We want to outline some of the biological effects of ionizing radiation, and I don't know how much detail we need to go into for that. I'm going to need a little bit of feedback on what you already know from a biology perspective. It got warmer already, right? Yeah, that didn't take too long. And then, I don't think we'll get to this one, but our next objective, Patrick, is to explain why some nuclei are more stable than others. Alright, so alpha decay we've already talked about. Why is beta decay called beta decay? Well, why is a beta particle called a beta particle? Yep.
Was it the second one found?
Nope. What do you mean it's after alpha particle? Jordan?
Smaller?
No, the Greek alphabet goes alpha, then beta, then gamma, and then I have no idea what's next.
Alpha, beta, gamma, delta?
So a beta particle, an alpha particle is the same thing as a helium nucleus. Right? A beta particle is the same thing as an electron. Right? It's the same thing, two different names for the exact same thing. All right? So a beta particle, identical to an electron. Alpha particle, right, identical to a helium nucleus, not a helium atom. A beta particle, identical to an electron. From a simplistic viewpoint, beta decay is super simple. We have an unstable nucleus, it shoots an electron out, and it's more stable. And that's all it is. And we can keep track of that with our chemical inventory. So here we have a hydrogen-3, right? We call that tritium. It's one of the very few isotopes that actually has a special name. That's not just the same name as the element. So chemically I would write that, right? H for hydrogen, 1 for the proton number, 3 for the mass number, and that will spontaneously decay into a helium-3. Helium has 2 protons, right? And then the mass number is 3, and then we're also getting an electron added in, right? So I have my 2 products, and I have my electron. An electron, I usually like to put the negative sign there for electron. I don't know why I like to do that. Yeah, I know there's faces because right now we're on the simplistic view. I'll get to the more complicated view, right? Put your hands down, I'm going to do it. But we need to address did I mess up?
How does it come blue?
Okay, so this is the simple view right now,
Okay.
right?
Okay.
We're probably going to spend about 15 minutes on this, right? Did I mess up?
No,
Unless I messed up, I don't hear anything right now. What?
I just wanted to know if there was a reason why it had a special name.
What? Who has a special name?
That's pretty interesting. Yeah.
Oh, yeah, I know the hydrogen isotopes have special names. I don't know what the reason is.
They're pretty.
So the electron, right? We're not balanced right now, right? Our proton numbers don't add up because we need to address the proton number and the mass number of an electron. So the proton number of an electron, I don't know what you think it should be. What do you think it should be? 0 could make some sense because it's not a proton. What else could make sense? Because 0 is not right. Yeah.
1.
It's not 1. It's not 1, but it is minus 1.
Oh.
All right?
That makes sense.
Because I was actually kind of clever about this earlier. I said proton number, but I also said charge number, right? So an electron is not a proton, but it has a charge of -1, whereas a proton has a charge of +1. Jamie, you all right? And then the mass number of the electron, though, is 0. An electron is way less massive than a nucleon. It's closer to 0 than it is to 1. All right, Liam, go ahead. Recognize that I'm not done.
So the number on the bottom is the charge of the nucleus.
No, the number on the
For normal things that are.
yes,
Yeah, that's what I was.
yes, yes. You're right. Yeah, simple first, right? Now there is another thing that comes along that we'll get to momentarily. All right, so at a first glance, beta decay is very simple, right? Again, we have an unstable nucleus, it shoos away an electron, it's more stable now. All right, so now, what's the problem? Right, why do we need a more complicated view? Patrick, what are you seeing?
Well, just can we get a proton from nowhere?
Sitting at?
Can we get a proton from like nowhere?
Oh, how do we get a proton from nowhere? Okay, so maybe that's a weird thing. Jake?
They say that the number is supposed to be the number of protons, but if it's subtracted with each electron, like the one, so that would be like for the quiz, for example, we'd be like, oh, it has 1 proton, but now because we took away an electron, it would have 2.
Yeah. So there's a more complicated thing going on. I just need to grab another marker. Ryan, talk to that.
I was gonna say it looked like a neutron turned into a proton and an electron.
All right, what did Brian say?
It looks like a neutron turned into a proton and an electron.
Brian said that?
Yes.
Great.
That's a lot.
And we can tell that from the picture, right? Here's tritium, all right? It's got 1 red thing and 2 blue things, so we know the red thing's supposed to be the single proton that every hydrogen nucleus in the universe has. So the 2 blue things must be neutrons. But then for helium-3, right, we have 2 red things, 1 blue thing. So we can see, I mean, you don't even need me to tell you, we can see that, yeah, we had 1 proton, 2 neutrons, now we have 2 protons, 1 neutron. So yes, a neutron changed into a proton. That's exactly what happened. Now let's keep track of that with our chemical accounting. Oh, this one's not very good. All right, so we start with a neutron. What is the proton number or the charge number of a neutron? 0. 0. The neutron's not charged, right? Not charged, neutral. So it has a charge number of 0. This one doesn't work. What is the mass number of a neutron? Yeah, it's 1. Now, all right. So the neutron is changing into a proton, evidently. What is the charge number of a proton? It's 1. Yeah, it's 1. Oh, this one. All right. What is the neutron? What is the mass number, the nucleon number of a proton? And we are not balanced right now. Right? We have 0 and 1. So what do we have to add to 1 to get 0? Negative 1. What do we need to add to 1 to get 1? 0. So that's our electron, or our beta particle, whichever. We can use either one. This time I'll use beta since I used electron last time. All right, so yes, a neutron can change into a proton, and then we do create an electron as part of that. We actually create something else also. We create something else called an anti-neutrino. And we actually do have to know that.
What song is that? Like V with 2 little dots?
I think it's a U, N-U. It is almost like a V with a bar over it. I can't promise that I've written that perfectly. So any time that we're doing beta decay, anytime we're doing beta decay, we have to include this anti-neutrino. Now, let me say a little bit more about the anti-neutrino, and then we'll back up and see what other questions we have. So an we might not have heard of anti-neutrinos before, but I think we have heard of neutrinos. In fact, was it the beginning of last year that there were those neutrinos that we thought went faster than light, or there was some evidence they went faster than light? Was that the beginning of last year, or was that the year before? Yeah, if I was telling you about it, then it must have been last year that was going on, the beginning of last year, right? But those were neutrinos, not anti-neutrinos, all right? So not the same thing. Now, under the standard model of particle physics, right, there are actually a fairly minimal number of particles that make up everything else. But every one of those particles has a corresponding antiparticle, right? So this is an example of a particle and an antiparticle. In fact, I think there's 3 different kinds of neutrinos, and then each of those kinds of neutrinos does have an antiparticle. All of our other types of particles have antiparticles also. For instance, all right, an electron has an antiparticle, right? It has the same mass, it has an opposite charge, and I'm not sure about its spin or color, which are like the other 2 quantities that describe particles. But what do we call the antiparticle? A positron. A positron, right? A positive electron. Yeah. What's that?
call electrons negatrons?
Negative. We would have grossly different names for things if we fully understood them at the time that they were named. Right? In fact, electrons would be positively charged if we knew more about them when Ben Franklin decided they were going to be negative for no good reason.
Isn't that just arbitrary?
It was arbitrary, and unfortunately he picked wrong. Right? Why did he pick wrong?
Like, how is that?
How is it bad? Well, you know how we say electrons go from the positive terminal of the battery to a negative terminal of the battery? Do you think that really happens, that a negatively charged thing goes away from a positively charged thing and towards a negatively charged thing? No. And I was very careful over the last year to not exactly lie to you, but be creative in saying that the positive terminal means the higher energy per charge terminal, right? That's not a lie, but the positive terminal is positively charged, right? So Ben Franklin picked wrong, and we're stuck with it. And we're stuck with defining circuits as defining the direction of current as the direction that positive charge flows, when really it's negative charge that flows the opposite direction. So anyway, yeah, he picked wrong, and the positive terminal means a higher energy per charge terminal, right? You can strike those last 90 seconds from your memory. So electron, and then the antiparticle is the positron. There's a proton, right? The proton has an antiparticle. I don't even know what it's called. I think it's just called a negative proton, I don't know. But a neutrino and antineutrino, right, just antiparticles of each other. So if we have beta decay, whenever we do have a neutron converting into a proton and creating an electron, we also create an antineutrino. An antineutrino is just a ridiculously low mass particle. Okay? The first year I taught this course, which wasn't that long ago, maybe 6 years ago, 7 years ago, I don't remember now, I wasn't able to say that it is a ridiculously small mass particle because the jury was still out, right? Fairly even split in the physics community between very small mass and no mass, but now we can say very small mass, right? The jury's not so split anymore. Yeah, Jordan.
So we use like an anti-Higgs boson particle.
Is there an anti-Higgs boson particle? If the Higgs boson is a particle in the standard model, which I'm pretty sure it is, then yes, there would be an anti-particle version of that, at least that's my understanding. Alright, so we really can treat beta decay as this fairly simple thing, that we just shoot an electron out of the nucleus, but we want to appreciate that there's more to it than that, because electrons don't live in the nucleus, right? So there is more to it than that. But we do need to know that this antineutrino is created. Alright, let me give you another example, and you will need your periodic tables for this, and we'll move on to gamma decay. So while we're getting our periodic tables out, let's start with Jacob. Yeah, go ahead.
But if we add the antineutrino, then doesn't that mean that it's not balanced again?
Oh no, the antineutrino has no charge, and remember, I did say ridiculously small mass. These mass numbers up here are what's called in atomic mass units. That is something in this topic that we'll address. An electron, I might get this wrong, but it's something like 1/1000th of an atomic mass unit, like something like that. It's like not, it's big enough that we shouldn't totally ignore it, but it pales in comparison to an integral atomic mass unit, and this would be orders and orders and orders and orders of magnitude less massive still. So using this system, we're really just tracking nucleons when we're talking about mass. Liam.
What's the difference between a neutron and an antineutron?
What's the difference between a neutron and an antineutron? Is that what you asked?
Neutrino and an
Oh, yeah, so one of those, I think it's 4, it might be 5, one of those basic physical properties, charge, mass, color, spin, is the opposite. And I can't tell you which one it is. I don't know enough about particle physics to tell you that. Ask me next year, because next year with the new IB curriculum, there is a particle physics piece of the core nuclear physics topic. So I will have to know that for next year. I don't know that right now. Patrick.
What's the significance of the antineutrino?
What is the significance?
Yeah.
Without it, well, so I have an answer. I don't know if it's going to satisfy you or not. Without that antineutrino, momentum is not conserved. during that conversion of the proton into a neutron into a proton and an electron. Yeah, that's not a very satisfying answer, but that observation was the genesis of the discovery of of neutrinos in general, I think. All right, so let me give one other example, then we'll move on to gamma decay. One of my favorite elements is carbon. Right? Because a lot of me is carbon. And one of my favorite isotopes of carbon is carbon-14. Because I think like archaeology is pretty cool, and extinct like mastodons and stuff is pretty cool. And we use carbon-14, we use the ratio of carbon-14 to carbon-12 in organic matter to get a date on things that have died in the last few thousand years. So I like carbon-14. Carbon-14 is used to date things because it does decay into something else at a very precise rate. Now I've put in the nucleon number for carbon. What's the charge number?
6.
Yeah, it's 6, right? It's on the periodic table, and we probably just know that one anyway. Carbon-14 does undergo beta decay, okay, when it decays. So I would like for you guys to go ahead and determine what else is produced when a carbon-14 undergoes beta decay. Why are you questioning that? Like, we're going to go over it in a few seconds. Like, we're going to go because you're super unsure.
Yes.
Okay. Why are you super unsure?
Because then it wouldn't be one carbon
Oh, it doesn't decay into carbon-12.
12. Oh, okay.
Oh no, it definitely doesn't decay into carbon-12. As far as I know, we can eject neutrons off of things. There are very, very, very few isotopes that do that. And that's why it's not one of our 3 types of decay that we're going to talk about. In fact, the most common way that happens has one of my favorite science names in the world. It's called spallation. Spallation. S-P-A-L-L-ation. Very uncommon to just eject a neutron. There's an isotope of californium that's really good at that. That's the one that we used at Oak Ridge a couple summers ago. There's a few other ones also. All right, anyway. So what do we add to -1 to get 6? 7. What do we add to 0 to get 14? 14, and that is in fact nitrogen. Absolutely. Absolutely. Nobody's yelling at me. And the anti-neutrino. We cannot forget the anti-neutrino. All right, so there's a second example. I want to move on. I actually don't want to ask if there are other questions. Well, no. Let me say one other thing. So I know I get yelled at sometimes when I go through slides without commenting on them. This is all review. Right? So beta decay isn't just an electron shooting out of the nucleus. As we said, a neutron converts into a proton, and an anti-neutrino and an electron are generated when the neutron does change into the proton. Here's another inventory and another accounting of that. Now, it's also possible for a proton to convert into a neutron. And some of your medical isotopes, I bet, do that. But some of them do. So let's take a very quick look at that. This really is beyond the objective, right? For this, we're probably not going to see, SL questions about this, but it's worth mentioning, and for some of your presentations you're going to have this. So let's do it. So we start with the proton, right, and then we make a neutron. What's the charge number of a proton? 1. What's the nucleon number? 1. What's the charge number of the neutron? 0. And what's the nucleon number? Okay. So we have to make at least something else because we're not balanced right now. The mass number is balanced, but the charge number isn't. What do we add to 0 to get 1? Positive 1. Right? I heard 1 or 2 negative ones. I heard lots of 1s. The positive 1, right? And what do we add to 1 to get 1? 0. Okay, who's this? That's our positron, right? So that's our positive electron or positive beta particle, whichever you prefer. And then we do get a regular neutrino if we're doing that. Positrons are actually, so positron was the antiparticle to the electron. Those are not that bizarre. Those are used every day. Right? Yeah.
How is this sign from neutrino to the second to anti?
Oh, there's no bar. That should not have a bar on top. Thank you very much for that. Anybody ever heard of a PET scan? PET scan, PET scan, right? The PET stands for positron emission tomography. All right. So a PET scan always uses positrons. Yeah.
Aren't neutrons supposed to be more massive than
Aren't neutrons more massive? Yes, I believe so.
So then how is that, that's making it less massive?
That gets less massive. Yeah, okay. Maybe that's why. So this happens less commonly than beta minus decay, right? That's why when we talk about 3 types of radioactive decay, we talk about alpha, regular beta, not positive beta, and gamma. But you're right. Yeah, we can't talk about this yet. We need to go into topic 7.3 before we really start having that conversation about changing masses. What I will point out, though, is that it's not so simple as saying that a neutron is always more massive than a proton. It's not so simple as that. It depends how fast they're moving. It depends who is next to them. There are a lot of other factors. We can't just say that a neutron is more massive than a proton. But in general, I would agree with you. A neutron is more massive than a proton. All right, Brian.
Why is there no line over the V?
Oh, because it's a regular neutrino, not an anti-neutrino if we have positron decay. Okay, so let's move on to gamma. And then I'm glad that some of you are asking a lot of questions. I really like this stuff also. Okay, so again, for beta decay, really all that we truly need to be able to show is that we know that we are creating an electron. Consequently, the charge number of the other thing produced goes up by 1, and the mass number stays the same, and we do have this tiny anti-neutrino that's produced as well. Gamma decay is the simplest of all. All right? And the reason for that is that gamma is not a particle. All right? It's just energy. It's a gamma photon, right? Just like a visible light photon, an X-ray, microwave, right? A gamma ray has no charge and no mass. So gamma decay is the simplest. So let's look at the accounting for it first, and then we'll go back and look at some of these other points. So here we're starting with helium-3, the same thing I think that we produced a few slides ago. So we have helium-3. Helium always has 2 protons, and this particular isotope only has 1 neutron. So this helium-3 is unstable, and it gets a little bit more stable by emitting a gamma photon. And then what do we add to 0 to get 2? 2. What do we add to 0 to get 3? 3. Who do we have? We still have helium-3. It's actually the same isotope. Alright? Now, if we look at this picture, I don't know that this is exactly how it works, but I like this picture. We have our 2 protons and our 1 neutron, and they're kind of like separated a little bit, and then it is totally intentional that with the release of this gamma photon, those 3 nucleons get a little closer together. Right? So when they're more separated, that's supposed to represent a more energetic, a more excited state, a more unstable state. And then by releasing a little bit of extra energy, they get more stable. Just like that hydrogen electron did with the atomic emission spectrum. That single hydrogen electron got to a lower energy level. Right? It released some energy by giving off a photon. Same thing here. This nucleus releases a little bit of energy by sending off a photon. Okay? And then that comes along with some internal rearrangement of the nucleons. Yes, Liam?
So photons aren't particles.
Photons are particles, but they have no charge, and at least in most uses, including this one, they have no mass.
Is there an anti-photon?
Is there an anti-photon? Yep, I believe so. I believe so. Yeah, sure.
What's so special about lead that gives it the ability to absorb?
Oh boy, what's so special about lead that lets it absorb stuff? The only thing I'm aware of is that it's really dense. So like, what do you call it? The things you use when you're fishing that you tie to make the thing sink?
Yeah.
Like a sinker or something, is that what it's called?
Oh,
I don't think they're made out of lead anymore because lead's kind of toxic, but they used to be. And the only reason it's made out of lead is that it's super dense. So for its size, it's very massive. And it's very massive because its crystal lattice holds the nuclei of the atoms closer together than most other crystal structures do. So if we're trying to shoot something through a sample of lead, it's just more likely to encounter our nuclei and our electrons, right? Because they're just a little closer together. At least I think that's how it works. Yeah, Brian, and then I want to move on.
So if they did the Geiger-Morrison experiment with lead, it'd probably be a lot less successful.
A little bit less. I don't know that it's a huge difference. And remember, we're only talking about 15, 20 atoms wide anyway. So I think there would have been pretty similar results, except that they didn't have the technology to get the lead as thin as the gold. All right, I would like to actually, I would like to skip this video clip. But, I won't skip it. I'll just talk quickly about it. And I'll talk while I'm finding it. So a gamma decay typically happens like right after a beta or an alpha decay. Right after an alpha or a beta, we have changed the structure of the nucleus a little bit. So that nucleus, in order to get more stable, releases a little bit of energy. So gamma doesn't typically happen like as an isolated decay. It usually happens along with one of our other types. I'll turn the lights off, but this is just a simulation of a nucleus that's undergoing these decays. Some of the steps are kind of easy to see, some of the steps are kind of hard to see. Alright, so we see these like this yellow junk shooting off every once in a while. What do you think that's supposed to represent? That's our gamma, right? So it's kind of like a sine wave that comes out of the nucleus, right? So it's supposed to indicate that it's a transverse wave, like a gamma photon. And then I see some arrangements of two blue things and one white thing. What do you think that is?
Okay.
That's our alpha particle. No, it's four things put together, so that would be our alpha. But I did just see a beta. Let me try and get back to that. I think it was about here. Oh, there it is, right? A little tiny thing, right here, right? So that's probably our beta. And I don't know that this model includes the anti-neutrino. Sometimes I feel like I can see it. Sometimes I actually think it does include the anti-neutrino. I think for this particular decay, it probably shot the anti-neutrino like into the board, so it's kind of blocked. But look at what accompanies the beta decay, right? Gamma, get some gamma photons. Same thing. Oh yeah, there's two things, right? There's two red things. Maybe that's a beta particle and an anti-neutrino. Maybe it's two beta particles. I'm not sure. Let's just look for one more alpha. Right, there's our alpha, and at the same time that alpha got shot out of the nucleus, the other nucleons shifted around a little bit and released some energy with those gamma photons. Right? But I like that this model shows that some of the other nucleons do move around a little bit. That's entirely accurate. It's entirely accurate. All right. So yeah. So enough of that. So our next objective is never mind. Let's get a little bit more practice with our three types of decay, and then we'll move on to a few of the properties of these three types of decay. I have a number of decay, like incomplete decay reactions for you. Most of them, actually.